Hello everyone, my name is Georgios-Petros and I'm a PhD student at ETH in Zurich, and I'm very happy to present to you our work, which is about a study that we conducted on bugs found in infrastructure as code ecosystem. We did this work in collaboration with Thodoris, Sotiropoulos, Georgios Alexopoulos, Dimitris, Mitropoulos, and Zhendong. So let's get started first with some background. So what is infrastructure as code? With this term, we refer to technologies that we use that automate the provisioning and the management of IT infrastructures. And the main advantage of IAC is that they reduce manual intervention and they ensure consistent and reliable deployments. And IAC have been widely adopted in industry, both in DevOps and in cloud computing practices. So we can classify infrastructure as code into two categories. First of all, we have the configuration-based IAC, which are used to manage resources on individual systems that are part of a broader infrastructure. And we also have cloud provisioning IAC, which are used to manage cloud resources. So in this work and in this presentation, we will only focus on configuration-based IAC. So in this context, DevOps engineers and system administrators write high-level declarative configuration files using domain-specific languages in order to specify the desired state of the infrastructure. Here we can see an example of an IAC program that is written in the DSL of Ansible, and this program describes the process of installing, configuring, and starting an Apache 2 service. So when we execute an IAC program, what happens beneath is that different configuration units are invoked. Configuration units are nothing more than libraries that are written in conventional programming languages, and they offer an API that can be used to describe the desired state of our infrastructure. And of course, we need to invoke them and supply them with some parameters that adhere to this API. So configuration units receive the desired system state from the IAC programs, and then they also read the current system state of our infrastructure, and then they check for deviations between the current and the desired system state, and then they update the system accordingly. In our example, we invoke the package configuration unit to install the Apache 2 package, and in the same manner we invoke the template and the service configuration units. So essentially, we can say that an IAC program is a structured combination of different invocations of configuration units. And of course, the domain-specific languages that we can use to write IAC programs also offer some features that we can see in traditional programming languages like loops and conditionals. And there exist a lot of ecosystems that facilitate the reuse of both IAC programs and configuration units. So the reliability of IAC software is of paramount importance because it is used to manage global infrastructures. And the bug in IAC can lead to devastating and costly production incidents, such as outages, data losses, and security vulnerabilities, and can impact millions of end users. However, surprisingly, despite the importance of ensuring that we have a reliable IAC software, there is limited tooling around this purpose, and mostly developers rely on traditional test techniques. However, these techniques omit to capture subtle bugs. And with that bear in mind, we want to conduct the first qualitative and quantitative study on bugs found in infrastructure as code ecosystems, and our goal is to provide a comprehensive taxonomy of IAC bugs that can help both developers and researchers understand the nature of the bugs and also guide the development of automated detection techniques. So we have 4 research questions. First of all, we want to identify the main symptoms of IAC bugs. Then we want to try to group those bugs into categories based on the root causes. Then we want to see how are those bugs triggered, and specifically the extent to which they depend on the current system state or the test inputs. And finally, we want to see how are those bugs fixed. So to answer our research questions, we selected the 3 most popular configuration-based IAC solutions, namely Ansible, Puppet, and Ceph, and we targeted bugs that are found both in configuration units and in IAC programs. Here we can see an overview of our methodology. So first of all, we access the official package registry of each ecosystem and retrieved all the repositories that are hosted and have associated with issue trackers. Then, out of those issue trackers, we retrieved all the issues that are closed and are linked to one pull request or commit. And then we performed an analysis in an iterative fashion. In each iteration, we selected a random sample of 60 bugs, 20 from each ecosystem, and then 2 researchers manually and independently analyzed and categorized each bug based on our RQs, and then an additional researcher validated our categorizations. And in total, we analyzed 360 bugs. Let's see now the results of our bug study, starting with the symptoms. Here, so in total, we identified 6 distinct symptom categories, and here you can see the distribution. So the most common symptom is external configuration failure. In this case, the IA component fails to perform an external operation, such as to execute an external command to the system or perform a remote communication. When this happens, the program terminates gracefully, although unsuccessfully, and we receive a message related to this external failure. To adduce an example, consider this snippet where when we invoke the PostgreSQL info configuration unit in order to retrieve some information from a database. So we would expect that we would retrieve successfully information about the instance of the database. However, what happens is that this script fails and we receive an error related to an execution of an SQL command. And this happens because within the code, we try to execute an SQL operation to the external database, which has a syntax error. Moving on to the second most common symptom, which is misconfiguration. So in this case, the IA component terminates successfully, although it fails to bring the system to the desired state. To adduce an example, consider this snippet. Here, we try to deploy a Redis database, and we set a custom password. However, when we execute this snippet, there is a specific configuration file that is created, and this file contains the password, and it's readable by all users. However, we would expect that this file would only be readable by a Redis user and its group. Moreover, the third most common symptom is internal error or crash. In this case, the IA component terminates unsuccessfully and ungracefully, and due to an internal error that led to a crash. To adduce an example, consider this snippet. Here, we try to invoke a RabbitMQ service, and when we run this snippet on a specific version of Ubuntu, we get a Ruby-related crash. And this happens because a specific version of Ubuntu has a bug which was not anticipated by the configuration unit that we invoked and led to a crash. And instead, we would expect that the configuration unit would be able to handle this issue gracefully. So the main takeaway of our symptom analysis is that IA bugs mainly lead to abrupt program terminations. And in order to detect such issues, a simple test oracle could include checking the exit status code of our program, and if it's non-zero, then this is an indicator of a bug. Now moving on to the root causes. In total, we identified 10 distinct root cause categories. Six of them were common in both configuration units and IAC programs, while 4 of them were appeared only in IAC programs. We won't go into every detail on each category, but you can find the details in our paper. What's interesting here is that the most common root cause is system interaction bugs. In this case, the communication between the IA component and the external system is not the intended. And to adduce an example, consider again the PostgreSQL bug that we saw previously, where in this case we were executing an incorrect SQL command. And this is a typical example of a system interaction bug because the communication of our module with the external database is not the intended. The second most common root cause are compatibility bugs. So generally, both IAC programs and configuration units are OS independent, and they should be handled also and run properly across different variations and versions of their dependencies. However, we noted that in a lot of cases, either the configuration unit or the IAC program could not handle deviations of operating systems or dependencies. And to adduce an example, consider this Ceph script. Here we invoke the Vagrant plugin configuration unit on Windows in order to install a specific package. And when we run this script, we receive a Ruby-related crash. And this happens because in our code, at some point, we tried to retrieve the home directory of the user, and we use a Unix-specific command, which leads in a crash on Windows. And to fix this issue, the developers replaced this command with an OS-agnostic operation. And a takeaway that we can have from our root cause analysis is that it's very interesting and important to try to identify compatibility bugs, and the simple technique that we could use to detect those bugs would be to run a cross-platform or cross-dependency testing approach that we would test the same module across different variations of operating systems or dependencies, and if we identify any discrepancy, this is an indicator of a bug. Now, moving on to the third research question, specifically to the operating system requirements, we found out that nearly 1/4 of our bugs are OS sensitive. We say that the bug is OS sensitive in two scenarios. First of all, if it's only triggered in a subset of the supported operating systems, then we say that it's a version agnostic. Or if it's only triggered in a subset of the supported versions of operating systems, and then we say that it's version dependent bug. And to help you understand this, consider again the compatibility bug that we just saw. So this bug is only reproduced on Windows, and it's therefore a version agnostic bug. However, if it would be only reproduced in specific version of Windows or another operating system, then it would be a version dependent bug. Now, with respect to state reachability, we identified that almost half of our bugs are state agnostic. This means that they depend entirely on the user input, and therefore, theoretically, an input fuzzer would be able to capture those bugs. However, what is very interesting here is that the other half of bugs are state dependent. This means that they receive, in order to be reproduced, they need a specific user input and a specific state of our system. And here, we distinguish between bugs that have an unmanaged state and a managed state. And we say that the bug has an unmanaged state if, with prior executions, by running an IAC program or a configuration unit multiple times, we cannot bring the system in the state necessary to find this bug. However, for the bugs that have a managed state, we can use the same component to produce the system state which is necessary to find those bugs. And this distinction has a lot of, to help you understand this difference, consider this, the previous example that we saw about the Postgres SQL bug, where we were executing a wrong SQL operation. So this is an example of a bug with an unmanaged state, because in order to trigger this bug, a database should be up and running so that we will be able to query it. However, this configuration unit doesn't offer the functionality to create this database. If it would offer this functionality to have a managed state. And this distinction has a lot of implications for developing automated software testing approaches, because in order to find bugs with managed state, we can solely use the configuration unit or the IAC program to create test states necessary to find those bugs. But in order to find bugs with an unmanaged state, we have to come up with another technique that will be system aware and will be able to fuzz the system and exercise those bugs. We wanted to further investigate the bugs with unmanaged state, and we found out that the majority require specific file system conditions, or they require also services to be up and running in order to be reproduced. Now, with respect to the bug fixes, we measured the size of the bug fixes, both in terms of files and in terms of lines of code. And what we found out is that the majority of the fixes are small. It touches only few source files. And of course, this means that techniques such as automated program repair can be very promising in this domain. Finally, in order to validate our initial assumption that tooling around improving the reliability of IAC is very limited, we conducted a survey of evaluating whether existing testing techniques can detect a type of bug based on our root cause analysis. And what we found out is that there is limited tooling around finding configuration unit bugs. And this, and recall the state reachability figure that we showed, we think that the researchers are not able to develop techniques to find configuration unit bugs because they are harder to reproduce. And this can be attributed to the fact that the majority of them are state dependent, as you can see here. And therefore, it's more challenging to develop a testing technique that will fuzz the system in addition to the user input. However, I argue that bugs in configuration units are very crucial and are more crucial than bugs in IAC programs, because a bug in a configuration unit will propagate to all the IAC programs that that use it, and therefore it's more foundational software. So my presentation has come to an end, and I will be very happy to answer any questions.
Hey, this is fantastic work. Thank you so much for the talk and the results.
Thank you.
I was curious, how many of the, so like it's a two-part sort of question, but like how many of the bugs that you analyzed, 350 or so, were you able to reproduce yourself? Did you actually try to run any of them yourself, or were you mostly just analyzing them based on the characteristics that you saw in the issue reports?
So, if I understand correctly, the question is if our analysis was based on only on the bug reports, right?
Right. I mean, I'm just curious. Did you try to like run them and reproduce them? Because I know in RQ3 you talked about state. Sometimes you need some external state, etc. But like, did you just manually look at the issues to figure this out, or did you actually run them? And how many of them were you actually able to reproduce the bug on your own in your own system or somewhere else?
We didn't try to reproduce the bug, but what we did is that in addition to looking at the bug report, which generally bug reports, they use standard practices on how to report and validate that this is indeed a bug and not there's some issue, other issue. And also, what's important is that for some categorizations, we also inspected the fix that is associated with its bug. And for example, generally, the way that the IAC software is structured, there are, for example, specific files that are related to some executing the IAC software in a specific operating system. So if we saw that the fix only touched files that are specific to an operating system, then this was an example of an OS specific bug.
Sure. So just to follow up on that, because you said that, like, as a conclusion of your analysis, you said that maybe we can have tools that can do some fuzzing and automatically like try different configurations. So how hard is it, do you think, to build such tools? Because you'll have to actually run all of these configurations with different operating systems, etc. Right? So right now you've been looking at existing bugs. Maybe some person just was building their that software on their own machine and figured it out. But how easy or hard is it for a researcher to run hundreds of configuration files to build a fuzzing tool?
Yeah, this is a very good question, because I believe that it's indeed very challenging to find such bugs, because aside from the user input, in this domain we also have the system state, which is very important to trigger those bugs. And also what makes testing very challenging is that there is a wide variety of different programs. There are others that are related to databases, others that are related to network configurations, or to start, for example, related to starting DNS servers. So it's difficult to have a generic technique to capture all the different types of bugs. But what's very interesting is that all of those libraries act as wrappers of other systems beneath. For example, they configure a database, so maybe interesting test oracles can come up by taking this wrapper aspect into consideration.
Okay, thank you so much.
You're welcome.
I know there's one more question, but I want to make sure we can wrap up on time. So maybe we could take the last question offline. If you could stick around for a couple of minutes. Let's have one more round of applause for our speaker.